we ended with the mechanism for an EAS reaction. So we've got the general mechanism written up. What does your aromatic ring act as in the course of this reaction?
The electrophile.
Close, as far as volume goes. It's the nucleophile, and then you're going to be reacting that with some electrophile. And we're going to run a substitution reaction in that process to put on that electrophile. It's a good thing I put it on nice and proper bond angles and everything. In the course of the reaction, your nucleophile will donate its electrons up to the electrophile. You generate those sigma structures. We have to draw all of those sigma structures because when we're doing a resin, or when we're drawing out a mechanism, we're trying to predict the minimum flow of electrons, okay, as easy as possible. We don't want to start breaking bonds if we don't have to right away. We'll start with our pi bonds, which kind of that weird gray area between an official bond and not a real bond. Okay? So we want to move those electrons around first. We find out that we can't permanently stabilize the cation. So we then can shift to breaking a sigma bond. We can break that hydrogen off and form your bond, okay, or restore aromaticity to the structure. And one of the things that we talked about was, now that we understand how the reaction works, can we make it go faster? Right? And what were the two things that we talked about as possibilities for making the reaction go faster? What was that?
Make the electrophile more positive.
We can make the electrophile more positive, or
More negative.
make the nucleophile more negative. So we're going to address both of those properties, and ultimately the chapter spends a lot of time discussing each of these things and how you're making each one more negative or more positive. Okay, so it's a little bit repetitive in the textbook, but it's going back to very similar patterns. You're just applying these patterns again and again and again and again. Okay, so it's ultimately just resonance with now a new structure, and it all of a sudden looks different. But it's still just a resonance contributor, and that's how we're going to predict our chemistry. We also ended last week trying to make the nucleophile more negative, and we did that by changing an atom on it. So instead of having hydrogens, we went through and swapped out that hydrogen for something else. In the case of making our nucleophile more negative, we put in atom X, and what was a characteristic of atom X that made our nucleophile more negative?
More electrons in hydrogen.
Our atom X had to have more electrons than hydrogen. Okay? That's going to speed our reaction, so we would refer to atom X in that case as an activator for the overall reaction. Okay? So now we're going to back away from the nucleophile and look at all the possible electrophiles that we can work with. Okay? So, how can we make our electrophile more electrophilic? So I would say probably one of the bigger arguments is to make sure you can identify your electrophile. What is the most positive atom in the reaction that you're working with? That's going to end up being your electrophile. Just because it's positive does not mean it will be the electrophile, but it increases the odds. Okay? So we've got 3 potential electrophiles shown here. Which of these 3 is the most electrophilic? Okay, so the first thing I would do is go through and circle the atom that I think is the most electrophilic in each molecule. Okay, you said nitrogen. I'm happy to start with that one. What other atoms might be electrophilic in the other molecules?
One of the bromines.
One of the bromines is going to have to be electrophilic if I'm going to say there's an electrophile there. Okay, and the last one?
Carbon on the carbonyl.
Why the carbon on the carbonyl? There's a big electronegativity difference between the carbon and the oxygen that is further compounded by that chlorine also being present, drawing electron density away. So now that we've identified our electrophilic atoms, we now want to be able to rank these. Which one is the most electrophilic?
Nitrogen.
Why the nitrogen?
Gotta be positive.
It's formally positive, which is exactly what we need for an electrophile. So our nitrogen is probably the most electrophilic. Which one next? Why the carbon on the carbonyl?
Because
You have a greater partial positive on it because the two electrophiles pulling more of the density away from that carbonyl.
I like most of your statement, and I think the one part that I'm going to complain about was just a slip up. I mean, the higher electronegativities of the chlorine and the oxygens. Absolutely. Completely agree. Okay? Which then, of course, leaves us with our bromine. Okay, with that third. So our next approach, now that we've identified our electrophiles, is to come up with some way that we can make them more electrophilic. Please don't give me the answer. Okay, so what could we add to make them more electrophilic? Well, our nitrogen is already positive, so we'll leave that one alone. That's why I actually put it in the middle, sandwiched it on the other two. How can I potentially make either the bromine or the carbon more electrophilic? What's that?
Give them a formal charge.
How can you give them a formal charge?
Take away an electron from one of those bromines, leaves the other one positive.
Okay, so what you're suggesting is that we take these electrons, give them all to that bromine, which leaves this bromine as electron deficient, and it is now formally positive. I like that in theory. There's a big problem with that. Why would the first bromine take the electrons? Bromine's electronegative, right? So it should be pulling electrons. But it's going to pull electrons from what? Atoms that are less electronegative than it. Is bromine less electronegative than bromine? No. So we have to somehow cause that bond to get polarized. Okay, and there's a couple different options that we can use. We used one in the lab last week, but there's a more common one or a stronger catalyst as well. Okay. Take either of those. Anybody know the catalyst? Okay. So we can look at the one that we did not use because it's a really good catalyst. FeBr3. How does that act as a catalyst?
Accept one bromine and blue.
What accepts another bromine?
This cell is going to attack the bromine and break the bond to form a single bromine and another bromine attack the.
So I'm not hearing what is happening between our iron tribromide and this bromine. You're saying we're making a bond. What bond are we making? Where?
Making the iron and the bromine.
Yeah. We're making a bond between the iron and the bromine. Why make a bond between the iron and the bromine? So, things to address, positives and negatives. What charge is the bromine that's now taking electrons from the other bromine? Pretty partially negative. Okay? That's why it's taking those electrons away. If it's negative, what does it need to react with in our catalyst? Something positive. So you decided to make it with the iron. I like that theory. That's a good explanation. So let's kind of push it all the way there. Why would our iron be positive? We can look at the electronegativity of the bromines already attached to it, really pulling that electron density away. Iron is one of those transition elements. You've got lots of d orbitals, all sorts of positive charge on that atom. It's going to really start to pull electrons from your bromine. Okay? What we're looking at is effectively a coordination bond between the iron and the bromine. The problem with that is then bromine has how many bonds? Too many. So we're going to have to break a bond. So if we broke this down a little bit smaller, say we're taking the electrons from one of those bromines and sharing with our iron, and we've got that coordination. But now that bromine, blue bromine, has lost all of its electrons. Okay, so it starts to get frustrated, and what does it do? It needs to steal electrons from something. There's two places it can steal electrons from. Both of those are bonds. Take them from the bond that was just formed, or we can take it with the bond to the other bromine. What do? Take it from the other bromine. The net result is that we end up with iron tribromide, or tetrabromide, with a negative charge because it's now gained electrons, and Br+. That Br+ is now our electrophile that we can then put in with our aromatic ring. Okay? Bromine doesn't want to be positive, so it's going to try and grab electrons from the ring as quickly as it can. So we can get our bromination substitution to happen right away. Okay? What's the other catalyst that you could potentially use, the one we used in lab? It's a much weaker catalyst. And everybody remembers all the chemicals you used in lab, right? From all the hazards that you had to look up.
It's only like 20, so.
That's relatively fair. You used acetic bromine dissolved in acetic acid. How does this help?
Is that a carbon on a carbonyl act essentially like the iron acted and pulled on the bromine though?
Interesting idea. We've got the carbon on the carbonyl there, except there's an issue with that carbon.
Oh, that's me.
Resonance stabilized. Got the right idea. You're trying to find a positive. Is there another positive on a compound known as acetic acid? It's an acid. It has that hydrogen ion. Okay. The acetic acid helps to polarize a bromine molecule enough that we generate that positive bromine again that can then come in and react. Okay? Does very similar chemistry. All you're doing is finding those positives and negatives and helping to push them around. Okay? Questions on your bromine catalyst? What happens with the other side? Can we potentially catalyze that guy? What did we say was our electrophile in our last compound? Our carbonyl carbon. To make it more electrophilic, what do we need to do?
Could you replace that other carbon with something more negative?
Interesting idea, but we can do something easier. So in that case, what we're doing is a full-on change of the reagent. Okay, what we want to do is use something along the lines of a catalyst that does not permanently change our reagent. We can add in some other species that's going to help to polarize one of those bonds. So you get the right idea in changing that other carbon, but that is a substantial change. What we want to do is polarize the other two bonds. Okay? Between those two, which one, well, actually take your shot. Which one do you think is going to be easier to react with, the oxygen and the chlorine?
Oxygen.
Okay, why oxygen?
It's got the pi bond.
Yeah, the pi bond. It's probably easier to break that pi bond. So we could evaluate the pi bond chemistry and try and break that off. Okay, we cannot. How could we do that? Could add an acid, try and polarize it in that case. Problem with that is in the process of adding an acid, we can end up reacting the species as well. Okay, the choice of acids are not particularly easy with this. So we can go through with another catalyst. Angie had suggested. Aluminum trichloride. What's special about aluminum trichloride? We could go and just approximate that it's working the same way as our iron. Aluminum is metal, which means its charge is going to be typically positive. 3 electronegative chlorines, all pulling electron density away. Our chlorine can share its electrons across in that coordination complex. That chlorine then has too many bonds, so what does it do? Rip electrons even further away from our carbon. Okay? And we can end up generating, very similar to our last one, an aluminum tetrachloride with a negative charge. And then we have this species, which on the quiz last week I hid. How did I hide it on the quiz? Is positive charge stable? No, can you stabilize it? Through maybe resonance? We can take lone pair electrons on our oxygen. generate this species, the Acylation ion. Okay? If you remember from the lab assignment, we started off with identifying the most electrophilic atom, the most reactive one. And you guys all did very well with that. Okay? Then when it came to identifying the electrophile, in this case, with this electrophile, which atom is the most electrophilic? Our carbon or the oxygen? Can the oxygen accept more electrons? No. It cannot act as the electrophile. Just because it's positive doesn't make it an electrophile. You also must evaluate its chemistry. For it to act as an electrophile, it must accept more electrons. It cannot physically do that. What atom can accept electrons? Our carbon. So the electrophile, excuse me, the electrophilic species is the carbon in the Acylation ion. Okay. The catalyst is added to help polarize and remove that chlorine atom. We're allowed to form that positively charged carbon because it is resonance stabilized in the Acylation ion. Okay. Questions about that one? So the goal in each of these cases is to add some kind of catalyst to help polarize our bonds and make our electrophile more positive. Okay, so now what we're going to do is evaluate all of the possible electrophiles that we could work with. So I threw up another one here. Really, that should be aluminum in the middle. It's not that big of a deal. Okay, you would see it as aluminum. And we just evaluated what happened in this case. Our electrophile is a chlorine positive. Okay, very similar to our bromination reaction. What happens to start? The electrons from our chloride can coordinate to the aluminum. Now we have too many bonds to that chlorine. It has to steal electrons from our other chlorine. Whoops. And we end up generating our positive chlorine, our electrophile, and our aluminum tetrachloride, which can dissociate to give you back your catalyst. Okay? So in this case, your reagents are chlorine and aluminum trichloride, and the electrophile that you're using whenever you're trying to get that is Cl+. So you are just going to do a substitution of chlorine for a hydrogen. I do that backwards. I always say that backwards. Hydrogen for chlorine. Okay. There's two other big ways that we can generate some some electrophiles. We've got an R+, and if you notice in that last one should look pretty familiar. We've got our Acylation ion again. We've got that electrophilic carbon. Okay. How did we get that last one to occur? What did we put in? What were our reagents? This is for that last section. Any guesses? How can we make that electrophile? We literally just solved this one.
C2O.
And our aluminum trichloride. That's exactly what I was going to wait for. We need that R group. That R group can be pretty much anything. Okay, so you can look at long extended structures just to make you think that you're doing a different chemistry. That R group can be anything we want it to be, as long as we have that acyl chloride at the end. Okay? How do we get the R+? It's a little bit trickier. As a hint, we probably started off with an R group that was attached to something electronegative. Right? What's a good something that's electronegative?
Oxygen.
Oxygen. What's the problem with oxygen? 2 bonds. With our R group, we've only got 1 bond that's missing. So oxygen does make that R group positive, but then I'd have another bond to account for on the oxygen, which could make things dangerous. Okay? Looking at more chemistry. What I want to do is pick something that limits the amount of chemistry. So we can throw in a halide. Good halide to use that we already have seen works to be polarized away from a carbon. Cl. How can we get that bond to permanently break? Let's try adding aluminum trichloride. The result is that our chloride coordinates over to the aluminum. Problem again, pulls the electron density away from that R group, and we now have our electrophilic R group. That can then react with our aromatic ring. So what we're trying to do is take advantage of the exact same chemistry in all cases. You're trying to make that carbon or your electrophile more positive and come up with some way to put it on there. Okay. Oh, I did sequence that properly. So there are some possible other things that we could look at. Drawn out nicely. These last two carry a particular special name, mainly because we are now making carbon-carbon bonds, which we said was difficult. Remember, so long ago we had Grignard reagents to really do that. Okay? And both of them are using the same catalyst, aluminum trichloride. So, of course, the person that discovered this got to attach their name to it, and you've got the Friedyl-Crafts reactions. Right, you're looking at these two reagents. How can we differentiate between these? Should we call them both Friedyl-Crafts? Are they both putting on the exact same electrophile? No, different electrophiles, so they get different names. R group typically refers to just what? In general, what's an R group refer to? Just carbons. So we are looking at adding strictly just carbons. We've got an alkylation. So in our first case, R plus is a Friedyl-Crafts alkylation. How about in the next one? Are we adding just carbons? We've got that carbonyl also getting put onto our structure. It's not an alkylation, it's now known as an acylation. Okay? That functional group right here is commonly referred to as an acyl group, okay, if it's put on a larger structure. Okay? So we've got these two possibilities for our alkylations and acylations. There's some interesting differences in the chemistry. Which of these is going to generate a more stable positive? Alkylation or acylation?
I would guess the acylation.
Okay, why?
Possible resonance.
Yeah, we get resonance going back and forth between our oxygen having shared electrons in versus not. Why is that going to impact our reaction? Okay. For our electrophile to react with the aromatic ring, we must form the electrophile first. It has to have some stability associated with it. Okay. If we're going to compare these two reactions, the alkylation does not work quite as effectively as the acylation. And that has everything to do with the stability of that electrophile. Our R group there is not a particularly stable carbocation. It tends to coordinate fairly strongly with the chlorine that it was originally from, and it makes it much more difficult to react. Okay? So how can we speed up the alkylation reaction? And don't tell me switch to acylation. That's cheating. Well, if we can't touch the electrophile, what do we need to affect? The nucleophile. So it turns out our alkylation, or Friedyl-Crafts alkylation reactions, only work when we have a nucleophile that is actually activated. If it is deactivated, which we haven't discussed yet, a deactivated ring will not react in the Friedyl-Crafts alkylation reaction because it doesn't have enough electron density to overcome the lack of stability of our carbocation in the alkylation reaction. Okay? So that's what's happening on this next section. Your alkylation is relatively I don't know why I said mild, unstable. Okay? So because of that, we need a nucleophile that is reactive enough that it can actually cause our alkylation to work, or to cause that electrophile to be positive to react. Yes?
Wouldn't an alkylation reaction be more reactive because
They're more reactive if you form the carbocation. But if your carbocation is unstable, does it ever form? Okay?
that's why it needs the nucleophile.
And that's why you need the active nucleophile. So we have that super reactive electrophile. We have to get something to react with it. If your nucleophile is not particularly reactive, they never interact with each other.
And that's the purpose of the aluminum trichloride.
And the aluminum trichloride helps
To activate.
to activate both the alkylation and your acylation. Okay. But once we've said, okay, we've now got that, and we've got our electrophiles at least somewhat able to form, we still need the nucleophile to come in and react. And in the case of the alkylation, if our nucleophile isn't nucleophilic enough, it's not enough to overcome the equilibrium forcing enough of that R group to be positive. Okay. So your acylation, we have a more, I don't like the phrasing on that, a more active electrophile, not reactive, but more active. It's more active because its energy is dropped, which then means we don't need as strong of a nucleophile to react with it. So if we're going to look at trying to predict overall reactions, if our ring has a deactivating group attached to it, we're going to have to use acylation. If it has an activating group attached to it, we can use either. It's not going to matter which one we choose, because both of them will work. Okay? And it has to do with the stability of that carbocation, forming that electrophile. Questions about that? Okay. Other electrophiles. So previously we looked at using Lewis acids as our catalysts. So we added aluminum trichloride and iron tribromide, all of those fun things to help push that chemistry. And what was happening was our electrophile, or some part of our electrophile, was sharing electrons with a metal. Okay, that metal is acting as a Lewis acid. We could also go through and use Bronsted-Lowry acids to go through and activate an electrophile. So one of the more common electrophilic reagents, or electrophiles as far as EAS go, is something known as the nitronium ion, okay, NO2+. You'll see that show up in a lot of cases. It is also a classic deactivating group when it's attached to the ring. So how can we make that? It's a hint. We'll mix sulfuric acid and nitric acid. How many arrows I should put in this? Good. All right. So it's an interesting reaction. Probably one of my favorites. I can almost guarantee that you'll see it on the test. Okay. Any ideas why I might like this reaction so much? Yes, you're doing it in lab today, but that's not why I like it. You're doing it in lab today because I like it. What is nitric acid? You got a couple big answers. One stands out. What is nitric acid? It's an acid. Think back to 151 or 152 just because I can point. What else can you tell me about nitric acid? It's a strong acid, which by definition means it gives up that hydrogen, okay, as soon as we put it into water. What can you tell me about sulfuric acid? It's also a strong acid. Interesting. We're going to mix two strong acids, and they are somehow going to react with each other to make this ion. Okay, well, let's take a little closer look at what's happening in the reaction. What occurred to get to that middle stage, or intermediate? Let's try and think about some arrow pushing.
The O and the alcohol grabbed the H, or one of the H's of the sulfuric acid.
We took the electrons from our oxygen, shared with that hydrogen, which meant that bond broke. Results that come out of this. We now have H2O as an excellent leaving group. We also have that HSO4-. Why does this step of the reaction seem really, really bad? at least at first. What did nitric acid act as in this reaction? A proton acceptor, which is a base. We took a strong acid, which by definition gives up its hydrogens, and turned it into a base. How did we do that? We use a stronger acid. You can go through and evaluate the pKa's for each of these acids, and you'll notice that for sulfuric acid, the pKa is what? Bigger or smaller than nitric acid? It is smaller. I think we're looking at like -7 and -3. What does that mean? That means we can actually force the nitric acid to act as a base in the course of this reaction. That puts us in a situation where we now have an excellent leaving group. That leaving group leaves, and we're left with the nitronium ion. Okay, we've got the water and our sulfate ion floating around afterwards. So it's really an interesting reaction because of that. Guaranteed you will be asked that question. Okay? Do you have any questions about that reaction? Okay. We can generate another electrophile. Any ideas where this one's coming from? Does it look kind of familiar? What happens if we take sulfuric acid and we give it more sulfuric acid? We make it uber concentrated. Well, one sulfuric acid molecule, how much did I actually provide here? One sulfuric acid molecule can act as a base, take the electron or take a hydrogen from another sulfuric acid molecule, and we can end up forming again a very similar intermediate that we had with the nitronium ion, which I didn't show. We can kick off that water as a good leaving group, and we now have our electrophile with the sulfate, or it's not sulfate. How do you call that? Anybody know how to refer to that? Sulfonium? I think I got it. I think it's a sulfonium. Okay. So we now have yet a new electrophile. Interesting thing about our sulfonium ion. Okay. Once we attach it to the ring, okay, so once we put on, so let's say we had our reaction, we somehow put on our sulfonium ion. It turns out that this reaction is reversible if we add more sulfonium or more sulfuric acid. Okay? So if we go through very similar conditions, instead of it being fuming instead of fuming sulfuric acid, we can use a more dilute. I don't think it's dilute. I think it's just concentrated. Double check me on that one. Concentrated sulfuric acid. We can actually cause the reverse reaction. Whoops. And we can put a hydrogen back on our structure. Do you have it written down?
Yeah.
What does it say?
Dilute.
Dang it.
It's that way around if you do from like benzene to that. It's concentrated. It says fuming H2SO4.
Yeah, so to generate our electrophile, so if we go all the way up to our original situation up here, typically the reagents that you're going to see, or actually let me just draw this all out. Come on, erase. We could go through and start with a benzene ring. We could do our H2SO4. Substitution reaction, we now have our SO3H on our ring. We can do H2SO4 again. We can go back to our normal benzene. Okay? We have to specify what's happening with those H2SO4s. To get our electrophile, we needed a lot of acid to help force the formation of the electrophile. So what we end up doing is adding concentrated. So you might see it written out as conc H2SO4, but you might also see an extra layer of information there. Fuming H2SO4. Okay, why do we call it fuming? What we're looking at is dissolving H2SO4 in water. Okay, what happens if you've dissolved too much H2SO4 in the water?
hydrogen gas?
You start fuming H2SO4. The H2SO4 starts pushing back out of solution. What ends up happening? You see fuming gas. Okay? That means you've made it so concentrated that it's literally getting rid of the sulfuric acid. Okay? So that's typically a phrase that you'll see for that. In the reverse case, we don't want it to be fuming. Big issue with fuming sulfuric acid in almost all reactions. Sulfuric acid has a tendency of destroying things. So even with that benzene ring, if we put in too much sulfuric acid, we could destroy everything. Okay, so if we're going to do the reverse, we want to do dilute sulfuric acid, kind of minimize and help push that thing off. Okay? So this is the one reaction that we've looked at as far as EAS goes that allows you to do the reverse. Why would this be important? This becomes really important because that sulfate group, or that sulfite group, the SO3H group can now act as a blocker. Now if we go through to try and evaluate the reactivity, this position now won't do substitution because there's a position, something else already there. Okay, so in our EAS reaction, it has to be hydrogens on the ring. This sulfate reaction can be nice because we've removed that hydrogen and we can put it back on just as easily. Okay? Another electrophile. How can we make this one? Give you two answers for this. I like that idea, the halogen, and still not going to work exactly. And we can do our aluminum chloride catalyst. Good call. It's a good idea. One problem with that, the title says Bronsted-Lowry acids. What catalyst did you put in? This is a Lewis acid, not a Bronsted-Lowry acid. So while this is a possible way to get that, there's another way. How else can we make that while using a Bronsted-Lowry acid? So what we're specifying is that one of our reagents must be H+. You could get away with that, except the problem with putting on the alcohol is you're going to generate water floating around in your reaction. The presence of that water can be a bit dangerous. To a smaller extent, I believe, in those cases. I think those also have to be hotter. So we could do an alcohol. That is a possibility. But at the same time, we're also adding a strong acid. That could get a bit dicey. So it's worth at least mentioning. So we got the potential for an alcohol. How else can we get a positive charge? Where's that hydrogen in the product? So in Josh's option, we put that hydrogen on the oxygen to make a leaving group. Leaving group left, we've got our carbocation. Is there another way that we could add hydrogen to a structure? Say, what if I put it out here? Think about the reverse. We'd be taking off H+, right? Where would the electrons go?
Do you have a hydrogen shift?
Not quite that. Probably the hardest organic reaction. If we take these electrons and we think about the reverse, take our orange electrons, what do we want to move them towards? Electrons move where? We could have started with the propene with the double bond. Okay. If we react An alkene with a strong acid, we can generate that carbocation as well. So we've got now 3 different ways with Bronsted-Lowry acids that we could go through and make that carbocation. Once we've got the carbocation, it can then potentially react with the aromatic ring. Okay, so good call on the water, actually. So if we simplify that one again, we can look again at our sulfuric acid reacting with the alkene, generate our carbocation, and that could then react with our aromatic ring. Why not use something like HCl? What's the problem with HCl? The chlorine acts as a nucleophile. The chlorine would react with the carbocation instead of the aromatic ring. So the acid we have to add has to be a non-nucleophilic acid. Okay? Yeah, this one's a bit odd. It's more of an addition reaction. You're adding the aromatic ring across the double bond with a hydrogen. So depending on your viewpoint, it's kind of an odd reaction.
If you added HCl.
Huh?
If you added HCl, what would it?
HCl is strictly addition. Yeah, because you'd be adding a hydrogen and chlorine across the double bond. So that gives us something like, what, 6 or 7 substituents that we could now put on the ring, right? So you're going to take advantage of those 3 reagents to go through and put on different groups onto aromatic rings. The next big issue comes back towards, and you can use your notes, is going to come towards using, addressing the nucleophile as far as its chemistry goes, right? And that's where resonance comes into play. And so because of that, I'm going to make you guys do some resonance. You guys are going to get up and move around and do some talking with each other. So I'm going to go ahead and count you off and divide it up into 4 different problems. This way no one can work next to each other. We got 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1. So find each other and work on the quiz. Number 1s will work on questions. Okay. I do expect you to turn the quiz in today, so you'll get the last 5 minutes of class to actually turn those in. But I want to see those answers up here. If you're not going to be here, make sure someone from your group does write your answer up on the board. Yeah? What's the question? Let me pause. So, the intent of this exercise was to get you guys to see the value of being able to draw resonance. Right? For problems number, let me take a look, 1 and 2, 1 and 2 should have been a little bit easier as far as trying to decide how the aromatic ring reacts. Because at positions 1 and 2, you've generated electron density on the ring. You put a negative charge on the ring. Well, where would your electrophile react? Your electrophile is positive. You put the electrons between the electrophile and the ring at that position. You now have the first step of your mechanism. When you move to questions 3 and 4, 3 and 4 get a little bit trickier. The issue with 3 and 4, what happened? For those of you doing 3 and 4, what happened to the ring? What charge formed on the ring? A positive charge. We need our aromatic ring to act as a nucleophile. It has to supply electrons. When you look at the resonance structures, you find that there's positive charge on the ring. Well, what does that mean about the reactivity of the ring? Should it react as fast or slower? If the ring is positive, should it react faster or slower? It should react slower because it doesn't have that electron density. If we're now forced to say it does react, where's your electrophile going to go? It's going to go to the only positions that do not have positive charge. Okay? So you've got those possible answers for question 2 and the start of your sigma structures or your sigma complexes for all of them up on the board right now. Okay? As an extra credit question, you should be able to go through and tell me, based on what we talked about today, which of these is not expected to produce products. Okay, there is one reaction that absolutely should not go. Okay, so you can feel free to write that on your quiz, share it with everybody if you want. Okay, this is one of the new slides. We just addressed these issues. So the intent was that you guys were going to be able to finish this and write this all up on the board because you were all super confident with your resonance abilities that we could then start to summarize and look at the end results. Okay? What I've got drawn up here are two primary cases. The top case, atom X has more electrons than a hydrogen atom. If you go back through and look at the previous problems, question 1 and 2, what can you tell me about atom X? What is it for question number 1? Atom X, number 1, what is it?
Carbon.
Carbon. Does that have more electrons or less electrons than hydrogen? More electrons. What's the result? Look at your resonance structures. What charge makes it to the ring? Negative. More electrons than hydrogen, our ring becomes negative. What is that going to do to the speed of the reaction? It should go faster because it has more electron density. So we call it an activator. Where did you put that negative charge on the ring? What positions? Take a look at the negative charge in these structures. Where's the negative charge found? The ortho and para positions. So if atom X has more electrons than hydrogen, it's an activator, reaction goes faster, and we expect it to be an ortho-para director. Our substituent or our substitution should occur at that position. Sorry, that was the wrong way. Group number 2, what's atom X? Where's group 2? You guys are group 2. What's atom X? Nitrogen. Does nitrogen have more electrons than hydrogen? Yes. That means we classify atom X as an activator. Where does our substitution occur? The ortho-para positions. Take a look at the products. Where's your nitro go? The ortho-para positions. Okay. What if we go through and we change the structure a little bit more? Instead of atom X having more electrons, let's make sure it has less electrons than hydrogen. Hydrogen always comes in with 1 electron. If we get less electrons than hydrogen, what does that mean about the atom?
Positive charge.
Has to be formally positive. So what we've got as an example is atom X now has the positive charge. As groups 3 and 4 should have discovered, God, I keep going the wrong way. What can you tell me about atom X in group number 3? What is atom X?
Nitrogen, and it's positive.
It's a formally positive nitrogen. If it is formally positive, does it have more electrons or less electrons than a hydrogen? Less electrons, which means when we go through and look at all of the resonance structures, what charge builds on the ring? Positive. How does that affect the speed of the reaction? It's going to slow it down. Why would it slow it down? For the EAS reaction to occur, what do we need the ring to have?
Negative charge.
Electrons. If atom X takes electrons away from the ring, our ring no longer has the electron density to be able to react. So first off, it will absolutely slow down. The trickier part is then if it's forced to react, where does it go? Well, when you look at your resonance structures, the ortho and para positions are covered in positive charge. Those positions cannot physically react because of the positive-positive propulsion between your resonance structure and the electrophile. That leaves you only 2 other positions. Those 2 other positions don't have any charge, which means they shouldn't react fast. Okay, go figure. That's why it's a deactivator. Okay? And those 2 positions happen to be equal to each other with their names. They're the meta positions. Okay, so if you take a look at the products for question 3, you'll notice that the bromine was put in the meta positions. For group number 4, what was atom X? That's you guys.
Yeah, I don't know.
What was atom X? Okay, so how about the rest of the class? Let's take a look at atom X. Where is atom X in these structures? Describe it to me. It is the atom immediately attached to the ring that is not our hydrogen. So, group number 4. What is atom X? Yeah? What was it? It's carbon. Does carbon have more electrons or less electrons than hydrogen? Has more. It's a bit odd. Is there something else going on with your structure? What was that? Was the carbon partially what? Positive. Why? The electronegativity of the oxygen draws electron density away. What charge builds on that carbon? A partial positive. That carbon has less electrons than hydrogen. What does that do to the overall reactivity? That makes that group have less electrons than a hydrogen atom, which means our reaction goes slower. Atom X was a deactivator, and we would expect our product to form in the meta position. If we go through and take a look at our answers, sure enough, that's where the CH3 was put, at those meta positions to our carbonyl. Okay? Everything in the EAS chapter comes back to being able to evaluate these resonance structures. If you don't know how to do resonance structures, this is the perfect time to start learning because you will need to have it mastered by Monday. Okay? So go through, pick any structure you want, start to look at those resonance structures to try and predict what's going on. Okay? So we will pick up there on Wednesday.